This is part 2 of the exam 4 review, so we're picking up where we left off. We've gone through 25 problems already. We're picking up with number 26. Here we're told to find the exact value of the logarithmic expression. I want you to do this, or you should be able to do this without using your calculator. What we're going to use is the inverse property that says if you have log base a of a to the x, that's equal to x. So we need to figure out how we can rewrite this as a power of 7 because the base of this log is 7. So 7 raised to what power is 343? 3. So we could write this as log base 7 of 1 over 7 to the third, but that 7 to the third needs to be in the exponent. What would this look like if I rewrote this as log base 7 of 7 raised to what power? Negative 3. So what is this log equal to? It's equal to negative 3. That's using the inverse property of logs. On 27 through 29, the instructions are to write the sum and or difference of logs and express powers as factors. What this means is I want you to expand this completely. The easiest way that I've found to do this is to start by rewriting the argument of the log as a product of powers of bases. So log base 10 could be rewritten as log base 10. And do I need to write this base here? I really don't, because if I don't write the base, then we assume that it's a common log. So I could just write log of 17 times x raised to what power would give me that square root? 1/2. And how would I rewrite this y with an exponent so that it could be moved up to the numerator? Negative 1. When you rewrite the argument as a product of powers of bases, then all you have to worry about is the product rule when you expand. So this would be log of 17 plus log of x to the 1/2 plus log of y to the negative 1. Then using the power rule, we can bring these exponents and write them down in front of the logs to get our final answer. Our final answer would be log 17 plus 1/2 log x minus 1 log y. And there's no need to write minus 1, just put a negative. Using the same process on number 28, I could rewrite this log as log base 6 of x minus 3 times x raised to what power? A negative 6. So now my argument is just a product of two terms. And I would rewrite that as log base 6 of x minus 3 plus log base 6 of x to the negative 6. Can I split this up by distributing the log base 6 across the subtraction? No, you cannot. That argument of the log cannot be messed with unless you use the product rule or the quotient rule or the power rule. We don't have a rule for distributing logs across parentheses. So my final answer here will be log base 6 of x minus 3 minus 6 log base 6 of x. On 29, the exponents get a little more tricky because I have a product underneath this radical. I might do this in two steps. So this would be log of the product ab raised to the 1/3 power times c raised to the negative 5. Now we have a distributive property of exponents that says if you have a product raised to a power, you can distribute that power across the product. That's the property that I'm going to use right here to rewrite this. So I'll rewrite this as log of a to the 1/3 times b to the 1/3 times c to the negative 5. How many logs will I have added together in my final answer? 3 of them, because I've got 3 terms here that are multiplied together in the argument. So this will give us log of a to the 1/3 plus log of b to the 1/3 plus log of c to the negative 5. Then your final step will be to move those exponents down in front of the logs using the power rule for logs. So this will be 1/3 log a plus 1/3 log b minus 5 log c. When you use this process of rewriting the argument as products of powers, it takes care of the quotient rule. You don't worry about making a mistake with the quotient rule and putting a negative in the wrong place. So all I'm using is the product rule here and then the power rule. Now we're going to go in the opposite direction. We're going to express each of the following as a single logarithmic expression. So I just follow the same steps in reverse order. Now this 1/2 right here is out in front of the log. So what's the first thing I need to do with this 1/2? Distribute it. When I do that, I get 1/2 log base 7 of x minus 3 minus 1/2 log base 7 of x. Now what can I do with these exponents? Put them up as a power on the arguments of the logs. And when I do that, I get log base 7 of x minus 3 raised to the 1/2 power plus log base 7 of x raised to the negative 1/2. Now I combine these using the product rule and write this as a single log. This will be log base 7 of x minus 3 raised to the 1/2 times x raised to the negative 1/2. How do I make this negative exponent positive? What do I do? Put it under this right here. So when I do that, that gives me log base 7 of, now I'm going to write this as an exponent. This will be the square root of x minus 3 divided by the square root of x. Because we have a distributive property for radicals that says if you have the square root of a divided by b, that's equal to the square root of a divided by the square root of b, I could rewrite this as a single radical, and my final answer would be log base 7 of the square root of x minus 3 divided by x. On 31, what's my first step going to be? Something to do with these constants out front. Move them into the exponent. So this will be log base 5 of m raised to the 3rd power plus log base 5 of n raised to the negative 8 power. Now what? I just used the power rule for logs. If you have n log x, that's equal to log x raised to the n. I took these numbers and I moved them up into the exponents. Now I can use the product rule, which says if you have addition between logs, you can rewrite that as a single log, multiplying those arguments together. So this is going to be log base 5 of m to the 3rd n to the negative 8. And then for your final answer, you don't want to have a negative exponent here, so our final answer would be log base 5 of m cubed divided by n to the 8th. Alright, on 32, what's my first step going to be? Power rule. We can rewrite this as log base 6 of what? X to the 3rd plus log base 6 of x minus 6 all raised to a power of 5. So our final answer will be log base 6 of what? X to the 3rd times x minus 6 to the 5th. On number 33, we have log base 4 of 112 minus log base 4 of 7. I want to rewrite this as a single log. That's going to be log base 4 of 112 divided by 7. Now we need to simplify this. What is 112 divided by 7? 16? So that'll be log base 4 of 16, but 16 I could rewrite as log base 4 of 4 to what power? 2nd power. Then we can use the inverse property, and what is this going to be equal to? It's equal to 2. When you have numbers in your logs, make sure you simplify as far as you can. In the next set of problems, the instructions are to solve the equation and round your answer to the nearest thousandth if needed. Well, first, notice that your variable is in the exponent. How do we get variables out of the exponent? With the power rule for logs, which means I'm going to need a log in here at some point. But before we're ready to do that, we have to isolate that exponential expression. Isolate it means get it by itself. So how do I get this 3 off of this 5 raised to the 2t minus 1? Divide both sides by 3. So I divide both sides by 3, and that's going to give me 5 raised to the 2t minus 1 equals 25. I won't have to take the log of both sides of this equation because it's possible to write 25 as a power of 5. How could I write 25? 5 raised to the 2t minus 1 is equal to 5 raised to what power? To the 2nd power. And that means because of the one-to-one property for exponents, if the bases are equal, then the exponents have to be equal. So the equation that I can solve is 2t minus 1 equals 2. This is just a simple linear equation. We can solve it by adding 1 to both sides, giving us 2t equals 3, and then divide both sides by 2, and we get t is equal to 3/2. What is the domain of an exponential function? All real numbers. Remember, the graph of an exponential function looks like this, right? The domain is all real numbers from negative infinity to infinity. That's important to note because that means that you don't have to check your answer when you get an answer. Of course, it's always possible to check your answer by plugging in a 3/2 in place of t and using your calculator. I can check my answer by doing 3 times 5 raised to the 2 times 3/2 minus 1, and that's equal to 75. So notice I typed in the left-hand side of the equation, and it's equal to the right-hand side of the equation. Whenever you're solving these equations, you shouldn't have to guess whether or not you got the correct final answer if you check your answer on your calculator. On 35, we have 4 raised to the negative x equals 1 divided by 256. 256 happens to be a power of 4. 256 is 4 raised to what power? 4 to the 4th. So I have 4 to the negative x equals 4 raised to the negative fourth. Why did I say this was the negative fourth and not 4 to the fourth? Because that 256 is in the denominator. When I move that base up to the numerator, I have to make that exponent negative. So now I have 4 raised to the negative x equals 4 raised to the negative 4. So negative x is equal to negative 4. What is x equal to? X is equal to 4. Can you check your answer on this one? Sure you can. I'm just not going to do it. On the next equation, we have 3 raised to the 6 minus 3x equals 1 over 27. Is it possible to write 1 over 27 as a power of 3? This is where knowing your powers comes in handy. 27 is 3 to the third power. So I could rewrite this as 3 raised to the 6 minus 3x equals 3 raised to what power? Negative 3. So the bases are equal, so I just set my exponents equal to each other and then solve for x. In order to solve for x, I'm going to subtract 6 from both sides, and that gives me negative 3x equals negative 9, and then divide both sides by negative 3. Remember, what you do to one side you have to do to the other, and that gives us x is equal to 3 for our final answer. On 37, I have 2/5 raised to the x. Well, I know I can write 8 as a power of 2, and I can write 125 as a power of 5. 125 over 8 I could rewrite as 5 raised to the third divided by 2 raised to the third. That doesn't quite look like what I have here. What I have right now is 5 halves raised to the third power using that distributive property of exponents. 5 halves doesn't look like this. How can I make this look like that? I have 2/5 to the x equals, what would make this 2/5 right here? What would I have to do to that exponent to get the fraction to flip? A negative exponent. Remember, negative exponents flip fractions. If I have a over b raised to a power, that's equal to b over a raised to the negative power. A negative in the exponent flips the fraction. So what is x equal to here? X equals negative 3 is our final answer. And you can always check that on your calculator, but on this problem, when you check it on your calculator, make sure you put the 2/5 in parentheses. So you have 2/5 raised to the negative 3, and use that negative sign here, not the subtraction sign. And then to change that to a fraction, we just hit math, enter, enter, and we see that we get 125 over 8. On 38, we can't write 2 as a power of 3, so we've got to do something different to solve this equation. If there's only one log in the equation, what do we have to do to get the log out of the equation? Do you remember the definition of logs? The definition of log says that y equals log base a of x if and only if a to the y equals x. This definition of logs allows us to rewrite this log as an equivalent exponent. If you only have one log in the equation that you're asked to solve, rewrite it as an exponent in order to get that log out of the problem. So what will be the base of my exponent? What is my exponent? Equals x plus 3. So we have x plus 3 is equal to 9 because 3 squared is 9. And then we subtract 3 from both sides, and that gives us x equals 6 for our final answer. On number 39, we have a natural log. What is the base of a natural log? No, the base of a common log is 10. The base of a natural log is e. Ln's and e's are inverses of each other. A natural log is a log base e. It may help if you actually write this step. This is log base e of the square root of x plus 2. Because there's only one log in the equation, we're going to rewrite this as an exponent. So what will my exponent be here? Yeah, what will the base of my exponent be? E to the equals x plus 2 to the 1/2 power. How do I get that 1/2 power off of here? What undoes square roots? Square both sides. We raise both sides to a power of 2. Well, what happens when you raise a power to a power? What do you do to the exponents? Multiply. 1/2 times 2 is 1. So over here we get x plus 2 to the first. I don't have to write that. And what is e squared squared? E to the fourth. To solve this equation, we want to get x by itself. How do I get that plus 2 off of the x? What do? Subtract 2 from both sides. What you do to one side, you have to do to the other. So those are going to cancel out, and I'm left with x by itself equals e to the fourth minus 2. Could I check this answer on my calculator? Sure I can. Do you want to see what it looks like? So on your calculator, you would hit natural log. I've got the square root of, what was x equal to? So I hit second ln to get the e. It's raised to the fourth power minus 2, and then we put plus 2. Do you see how this part right here is what x was equal to, e to the fourth minus 2? Then I have to put the plus 2. And when I put this in my calculator, I get 2, which is the right side of the equation. So we know we got the right answer. On number 40, we have a log base e equal to a log base e. If the bases of the logs are equal, what does that tell us about the arguments? They're also equal, so I could rewrite this then as 21x plus 4 equals 10. Now to solve for x, I subtract 4 from both sides, and that gives me 21x equals 6, and then divide both sides by 21, and I get x equals 6 over 21. Do I have to check this answer? What's the domain of a natural log function? Any non-negative number. This is the graph of a natural log. It passes through the point 1, 0. It's asymptotic here to the y-axis. The domain goes from 0 to infinity, not including 0. So that means that we cannot take the log of a negative number. I got a positive answer for x, and that positive answer is not going to make the argument of this log negative, so I do get to keep my answer. X is equal to 6 over 21. That does reduce to 2/7, and I would rather see the 2/7. On 41, what would I do in order to solve this equation? There's only one log in the equation. When you come across these problems on your homework and on your tests, look at how many logs there are. Here I had 2 logs, but it was a log base e equals a log base e, so I just set the arguments equal to each other. What did I tell you to do if there's only one log in the equation? If there's only one log in the equation, rewrite it as an exponent. How would I rewrite this log as an exponent? What would be the base of my exponent? Raised to what power? Equals x squared minus 6. 12 to the first is 12. What type of equation is this? Quadratic. And how do we solve quadratic equations? I set this equal to 0 by subtracting 12 from both sides of the equation. Once this is set equal to 0, what do I do? This one does factor pretty easily. What's one of the factors? So I get x minus 4 times x plus 3. So what is x equal to? Now remember, with logarithmic equations, you have to check and make sure that your answer is in the domain to see if you get to keep it. So I need to go back to the original problem. If I plug in a 4 for x, I get 4 squared minus 4. 4 squared minus 4 is 16 minus 4, and that's 12. So this answer gets to stay. When I check x equals negative 3, that gives me a negative 3 squared minus 3, and that's going to be 9 minus 3, and 9 minus 3 is 6. So both of these make the argument positive. I get to keep both of my answers for this particular problem. This is my check on the domain. We didn't have to do that with the exponential equations because the domain of the exponential equations is all real numbers. But logs have a restricted domain. They go from 0 to infinity, not including the 0. On number 42, I have log base 3 of x plus log base 3 of x minus 24 equals 4. If you have addition between logs, you need to rewrite that as a single log. So this would be log base 3 of what? X times x minus 24 equals 4. Once you get rid of the addition or subtraction between logs in an equation, you then see if you have a log equal to a log or only one log in the equation. For this problem, we have only one log in the equation. How do we solve an equation if there's only one log? What do we do? Rewrite it as an exponent. What will be the base of the exponent? Raised to what power? Equals x times x minus 24. Now we can distribute this x and simplify 3 to the fourth. So that's going to give us x squared minus 24x equals 81 because 3 to the fourth is 81. Now we're left with a quadratic equation. How do we solve quadratic equations? Set it equal to 0. When I do that, that's going to give me x squared minus 24x minus 81 equals 0. This quadratic will factor. We have x plus 3 and x minus 27. Because 3 times 27 is 81, a positive times a negative is negative, and negative 27 plus 3 is negative 24. That means that x is equal to negative 3 or x is equal to 27. Now you have to check your answers to make sure that it's in the domain of the problem. Looking at the original problem, I have negative 3 for x, and x is an argument by itself. Can this negative 3 work? Can I take the log of a negative 3? So I don't get to keep that answer. Just because one works doesn't mean they're both going to work. When x is equal to 27, It works there, and 27 minus 24 is positive. That one works, so when we check our answer, we see that 27 is the only solution. The negative 3 here was an extraneous solution. On 43, we have addition between the logs. We begin by removing that addition between the logs and rewriting this as a single log. That means that I can rewrite this problem as log 3x equals log 5 times x plus 5. What's the base of this log? If there's no base given, what is the assumed base? It's 10. And what do we call this log? A common log. LNs are natural logs. Logs without a base are common logs. So I have a log equal to a log. The bases are equal. That means that the arguments have to be equal. So we get 3x equals 5 times x plus 5. What do I need to do first in order to solve this equation? Distribute the 5, and that gives us 3x equals 5x plus 25. Now what? We could subtract 25 and subtract 3x, but it's easier just to move all the x's to one side, so I'm going to go ahead and subtract 5x from both sides, and when I do that, I get negative 2x equals 25. Now what? Divide both sides by negative 2, and that means that x is equal to negative 25 halves. If x is equal to negative 25 halves, I have 3 times negative 25 halves here. Can I keep this answer? No, I can't, because it makes the argument negative. So we would say that there's no solution here. On number 44, we have subtraction between the two logs. How would I rewrite this as a single log to get rid of the subtraction between logs? This would be log of what? 2 plus x over x minus 3 equals log 2. Now we have a log equal to a log. The bases are equal, therefore the arguments must be equal, and we have 2 plus x divided by x minus 3 equals 2. Whenever you have a fraction in an equation, you can get rid of the fraction by multiplying both sides of the equation by the least common denominator. In this case, that's x minus 3. What you do to one side, you have to do to the other. When we do that, this x minus 3 is going to cancel out, and then I can distribute this 2, and we get 2 plus x equals 2x minus 6. Now it's just a matter of solving a simple linear equation. So I'm going to subtract x from both sides of the equation and add 6 to both sides of the equation, and that gives me x equals 8. If I plug in an 8 in place of x in the original problem, I get positive values in the argument. Just make sure you check that. On 45, we have e raised to the 4x equals 2. That variable is in the exponent. Remember, e is not a variable. How do we get variables out of the exponent? What do we have to do to both sides of the equation? Let's take the natural log of both sides of the equation. What is the natural log of e raised to the 4x? So we get 4x equals the natural log of 2. How do I get the x by itself? Divide both sides by 4. So that means that x is equal to the natural log of 2 divided by 4. Can I cancel this 2 and this 4 and say that this is the natural log of 1/2? No, you're not allowed to touch that argument of the log unless you're using the product rule, the quotient rule, or the power rule for logs. This would be your final answer. On 46, we have 5 raised to the 3 minus x equals 20. The variable is in the exponent. How do we get a variable out of the exponent? Let's take the natural log of both sides of the equation, and then we can use the power rule. When I use the power rule, this power gets moved down front. That power is a binomial expression, so I have to keep that power in parentheses, and I get 3 minus x natural log 5 equals natural log 20. Natural log 5 is a constant, just like 4 is a constant, or 2 is a constant, or square root of 7 is a constant. What do we do when we have a constant multiplied outside of parentheses like this? We distribute it. So I'm going to distribute that natural log 5 to both sides of the equation. See, if it doesn't make sense when it's written as something complicated, think about something simple. Like if I had x plus 2 times 7, if I wrote that, you would have no problem seeing that you need to distribute the 7. This is confusing because you see letters mixed in with numbers, but natural log is a mathematical operation just like square root or addition or subtraction. So this is just a number. The natural log of 5 is a number. So when I distribute this, I get 3 natural log 5 minus x natural log 5 equals natural log 20. The goal in solving this equation is to get the x by itself. This is a constant minus x times another constant. I want to get the x term by itself, so what do I do with this term? If I had 4 minus 3x equals 7, What would you do to solve this? You would subtract the 4. Well, that means I'm going to subtract the 3 natural log 5. Like I said, take something complicated and rewrite it as something simple where this is just a number. 3 natural log 5 is just a constant because there's no variable in it. This is just a number times x, just like this is a number times x. If you understand the process for solving something simple, in mathematics we use the same process. Don't let the complicated terms here fool you. So we subtract 3 natural log 5 from both sides, and that's going to give us negative x natural log 5 equals what? How do I simplify this? Are these like terms? They're not. In order to be like terms, the arguments have to be the same. So I just write them both down. It's the natural log of 20 minus 3 natural log 5. Now how do I get the x by itself? X is being multiplied by a constant. What undoes multiplication? And I divide both sides by what? Negative natural log 5. So I have x equals the natural log of 20 minus 3 natural log 5 divided by negative natural log 5. This is one where I asked you to round your answer to 3 decimal places. So we're going to need our calculator in order to do that. You have 2 terms in the numerator of this fraction, so you want to make sure that you put the numerator in parentheses. This will be the natural log of 20. Notice when you hit ln, your calculator automatically opened a parenthesis. For the argument, you need to close that parenthesis for the argument. Minus 3 ln 5. Close the parenthesis for the argument, then close the parenthesis again for the numerator, divided by negative natural log 5. And that gives us 1.139 if we're rounding to 3 decimal places. So this is approximately equal to 1.139. If I ask for the exact answer, this is what I want. If I ask for a decimal approximation, this is what I want. On number 47, we have 5/7 raised to a power of x equals 2 raised to a power of 1 minus x. All right, how do I get the variable out of the exponent? What did we do over here to get variables out of the exponent? Take the natural log of both sides. So I'm going to take the natural log of the left-hand side and set it equal to the natural log of the right-hand side. What you do to one side, you have to do to the other. Then we can use the power rule to bring these exponents down in front. So this will become x natural log 5/7 equals 1 minus x natural log 2. What will my next step be? Distribute. Distribute this natural log 2 to both of these terms. So that means that I've got x natural log 5/7 equals 1 times natural log 2 is just natural log 2 minus x natural log 2. Now there's 2 x's in the equation. I need to get them on one side. So I will add x natural log 2 to both sides of the equation. What you do to one side of the equation, you have to do to the other. And when I do that, I get x natural log 2 plus x natural log 5/7 equals natural log 2. Both of these terms have an x in common. Do you see that? Factor that common x out and you're left with just numbers. Natural log 2 plus natural log 5/7. And that's equal to natural log 2. Now how do I get the x by itself? Divide both sides by that giant piece right there, natural log 2 plus natural log 5/7. Can I cancel this natural log 2 with this natural log 2? Whenever you have addition or subtraction between terms in the numerator or denominator, you cannot cancel. If it was multiplied or as a factor out front, I could cancel, but if there's addition or subtraction between terms, I can't cancel. So I end up with x equals the natural log of 2 divided by the natural log of... Could I use the product rule to rewrite this as a single log? And that would be 10/7. And then I could use my calculator to get a decimal approximation. So on my calculator, I want to do the natural log of 2 divided by the natural log of 10/7. Make sure you close your parentheses for the arguments of the logs. And that gives us 1.943 for our decimal approximation. If I ask for the exact answer, this is what I'm wanting. If I ask for rounded to 3 places, this is what I want. Know how to do both. The last few problems deal with compounding interest, compounding periodically and compounding continuously. You need to have the compounding interest formula memorized. A is equal to P, where A is the amount that you have at the end of your investment period, P is your principal, times 1 plus R divided by N, raised to the nt, where r is your interest rate written as a decimal, n is the number of times you compound per year, and t is time measured in years. This is for compounding periodically. If we're compounding continuously, we use a equals p raised to the rt. Those are the two compounding formulas that you need to have memorized. There's a lot of memorization that has to happen with this test. We have a lot of different rules. So on 48, we're told that we have $1,000 invested at 5% compounded semi-annually for 7 years. What is this 1,000 going to be? That's our principal. R is equal to what? 0.05, because we have to write that as a decimal. Semi-annually means n is going to be equal to what? 2, because it's 2 times a year. N remembers the number of times per year that you compound, and then t here will be equal to 7. So we just drop these numbers into this formula and we get a is equal to 1,000 times 1 plus 0.05 divided by 2 raised to the 2 times 7. What you don't want to do is use parentheses for multiplication on your calculators. It tends to cause careless mistakes. So to do this on our calculator, we would type in 1,000. It's okay to use parentheses here, and we have 1 plus 0.05 divided by 2, close parentheses, raised to a power of 2 times 7, or you could just type in 14 if you know what 2 times 7 is. And we end up with $1,412.97. Usually the instructions on these will ask you to round to the nearest penny. On 49, we have $1,000 compounded at 5% interest annually. So what is n equal to? For 4 years. Dropping those numbers into the formula, we get a is equal to 1,000 times 1 plus 0.05 divided by 1 raised to the 1 times 4. You can simplify this and rewrite this as 1,000 times 1.05 raised to the 4th power. So on our calculator, we type in 1,000 times 1.05 raised to the 4th power, and we get $1,215.51. If you wouldn't have done this simplification in your head, you could have typed this in like we did over here. Just make sure that your parentheses are correct, otherwise you get an incorrect answer. And on the last problem, we're told, suppose that $16,000 is invested in a bond fund and the account grows to $18,552.21 in 4 years. Use the model A equals P e to the RT to determine the average rate of return under continuous compounding. Round to the nearest tenth of a percent. We're now looking for what variable in this equation? R. We have the equation A equals P e to the RT. Do I know a number that I can plug in place of A? The $18,552.21. Do I know a number I can plug in place of P? 16,000. E is Euler's number. It's a constant. Raised to the R times, what am I going to use for T? Right here, 4 years. So our variable is in the exponent, but this exponential expression is not completely by itself because it's multiplied by the 16,000. What can I do to get that 16,000 off of the E? Not subtract. This is 16,000 times E. What undoes multiplication? Division. So we divide both sides by 16,000. What you do to one side, you have to do to the other. When we do that, this goes away, and I end up with E raised to the 4R equals 18,552.21 divided by 16,000. I don't want to do this right now and get a decimal approximation because I'll run into trouble with rounding. I don't want to make any rounding errors. I only want to use my calculator one time to get my final answer when I have R by itself. The variable R is in the exponent. How do we get that variable out of the exponent? What do we do to both sides of the equation? We take the natural log of both sides of the equation. So that gives us the natural log of E raised to the 4R equals the natural log of 18,552.21 divided by 16,000. Ln's and E's are inverses of each other, so that's going to cancel out, giving me 4R equals the natural log of this argument. And how do I get the R by itself? Right, I divide both sides by 4. And when I do that, I get R is equal to the natural log of 18,552.21 over 16,000 divided by 4. Now I was asked to round my answer to the nearest tenth of a percent. So how many decimal places am I going to need if I need a tenth of a percent? To change that percent to a decimal, I just moved that decimal over 2 places, so I need 4 decimal places in my answer. So we hit the natural log of 18,552.21 divided by 16,000. I'm going to mention this because it's come up before as a point of confusion with the calculator with a student that wasn't very familiar with how calculators work. When I write 16,000, I put that comma between the 16 and the 0. You don't use this comma button on your calculator and put commas there. It confuses the heck out of your calculator. You will get an error message every time. So I've got this natural log. The argument is now in parentheses, and then I divide the whole thing by 4. And I need 4 decimal places, so this is going to be 0.0370. Now you want to write your answer as a percent because it was asking for your answer as a percent, and that's going to be 3.70% interest. And that would be your final answer. And this wraps up the review for exam 4.